number 7. Estimation of the range of validity of Beer-Lambert law in solution of Cobalt solution, Cobalt 2 plus solution. Okay, first of all we have to know the Beer-Lambert law. There are two scientists, there were two scientists, one was Beer and other one is Lambert. Beer stated that absorbance, so imagine we introduce an particular radiation or light, UV or visible or IR or any radiation we will introduce into a particular solution which is in a vessel, some glass or quartz or anything. If the incident light goes through this solution, there may be a transmitted light, here the incident light. However, some of the radiation will absorb by this solution. Some of the radiation from this incident light will absorb the solution. That absorbance value A, that absorbance will depend on the concentration of the solution. Beer stated that, scientist Beer stated this thing, absorbance is proportional to the concentration of the solution. However, on the other hand, Lambert also observed one thing, this absorbance is proportional to the path length. Path length or this distance which the incident light travelling. So transmitted light travelling this distance we call that path length. Path length. So he stated this absorbance is proportional to the path length. Combining these two, Beer and Lambert, we got another expression as Beer-Lambert law. Absorbance is proportional to both concentration and path length. I will state it in simple letters, path length. Okay, instead of this proportionality mark, මේ සමානුපාතික ලකුණ සමානුපාතික වෙනවා කියලා කිව්වා. මේ absorb මොකද්ද? මොකක් හරි ලයිට් එකක් සොලියුෂන් එකක් කරහා යනකොට ඒ යන ලයිට් එකේ කොටසක්, ඒ ලයිට් එකේ රේඩියේෂන් එකකින් කොටසක් මේ සොලියුෂන් එකකින් absorb කරනවා. යම්කිසි ලැම්ඩා මැක්ස්වෙල් ලැම්ඩාගයක් තරංගායාමයක් absorb කරනවා සොලියුෂන් එකේ. එතකොට එළියට එන්නේ ඊට වඩා අඩු තරංගායාම වල ඊට වඩා අඩු intensity එකක්. Here incident light intensity is very high. Intensity is high. This transmitted light intensity is low. යාගේ තීව්‍රතාවය අඩු වෙනවා. ඒ කොටසක් මෙයා absorb කරපු නිසා. මේ intensity initially higher intensity, finally lower intensity, that means part of the radiation absorbed by the solution. කොටසක් solution එකකින් absorb කරලා මේ absorb කරපු ප්‍රමාණය ඒ solution එකේ සාන්ද්‍රණයට සමානුපාතිකයි කියලා බියර් කියලා විද්‍යාඥයා කිව්වා. ලැම්බර්ට් කිව්වා ඒ absorb කරන ප්‍රමාණය path length එකට දුරට සමානයි කියලා. මේ දෙකම එකතු කරලා බියර්-ලැම්බර්ට් නියමය කියලා මෙහෙම එකක් ඉදිරිපත් කරා. මේ proportionality mark එක සමානුපාතික ලක්ෂණක් නැති කරගන්නේ කොහොමද? සමානුපාතික ලක්ෂණක් කියන්නේ සමානයි K කියලා වැලියු එකක්. Equal and constant. Okay, so instead of this proportionality mark we use equal mark and constant, we use epsilon and concentration and length. Here absorption, molar absorption coefficient කියලා අපි මේකට කියනවා. molar absorption coefficient එකක් කියලා කියනවා. This is the Beer-Lambert law. However, this law is valid until the absorption from 0 to 0.7. In experimentally we know Beer-Lambert law's validity range is absorbance value 0 to 0.7 absorbance. This absorbance, maximum absorbance is 0.7. After that, Beer-Lambert law is not valid. That's the thing you have to remember. This is the validity range of Beer-Lambert law, 0 to 0.7 absorbance. Okay, keep this thing in your mind. Okay, now I am jumping to our experiment. Okay, we have provided a stock solution of cobalt. What is that? we have provided 1 m cobalt solution, stock solution, which is in a volumetric flask. It may be 100 ml, I guess, doesn't matter. 100 ml CO2 plus cobalt solution. Concentration is 1 m. 1 m means 1 moles per cubic decimeter, or 1 m. This is our stock solution. By using this stock solution, we will prepare dilution series. First of all, that we have to make 3 working solutions. This is stock solution. We prepare 3 working solutions or dilutions. What are them? .8. This may differ in your book. The concentration here, one is 0.8. Next one is it is 0.6, and other one is 0.4, 0.5. This concentration value is may be somewhat different in your book, okay? 0.5. However, by using this stock solution, we will prepare 3 working solutions. From these 3 working solutions, we will prepare another series of dilutions. One was 0.05. We have to use C1V1 equals C2V2 equation to prepare this dilution series. Okay, one solution is 0.05, other one is 0.1, 0.15, 0.2, 0.25. Okay, 0.3 and 0.4 is already been prepared. Okay, 0.4 and 0.5. We prepared that. 0.5 is already. 0.6 already we prepared, and 0.8 already we prepared, and finally 1 m, our stock solution. So we will get this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 and 11. We have 11 solutions. We prepared from this stock solution. By using this stock solution, we prepared 11 solutions including this stock solution. Okay, there are 11 solutions. That's the first objective. Now what will we do? We have to find out the lambda max, or maximum absorbance wavelength of cobalt. How can we do this? We have to use the spectrophotometer. I will erase this. Spectrophotometer. Spectrophotometer. Here there are so many spectrophotometers. UV visible spectrophotometers and normal visible spectrophotometers. There are so many spectrophotometers. Here we are using UV visible spectrophotometer because it can generate both UV and visible light. There are 2 lamps, 2 bulbs. One will emit UV light, other lamp, tungsten lamp, will emit visible light. Okay, there are 2 light sources in UV visible spectrophotometer. We can choose preferred wavelength, preferred lamp. Okay. In UV visible spectrophotometer, what should we do? Initially, we have to know there are two types of spectrophotometer: single beam spectrophotometer and double beam spectrophotometer. What is the meaning of this single beam and double beam? That means in single beam spectrophotometer, light will come from as a one. Light will come from one slit, and light will not divided into two parts. Light will come out only from one part. Okay, we will insert our sample into this spectrophotometer. We will introduce our sample. Here our solution, I will color it as green color. Here our sample, light will go through this. This is called cell. Spectrophotometer cell. This is spectrophotometer cell, that we call sample cell. These sample cells are produced by few materials. One was glass. These glass cells, we will use glass cells when we are dealing with visible light. When we are using visible light, we will use glass cells. Path length of these cells, every glass cell is 1 centimeter. Okay. When we observe from the above, the length and width both are 1 centimeter. 1 centimeter. Okay. This is our cell. So path length is 1 centimeter. However, when we are using visible light, we will use glass cells. However, when we are using UV light, we have to use quartz. We have to use quartz because glass will absorb UV light. Because of that, we can't use glass cells when we are using UV light. When we are using UV light, we have to use quartz cells. There are some another type of cells also, plastic, made up of plastic. However, these plastics are not using because sometimes when we are dealing with water and liquid aqueous solutions, when we are using aqueous solutions which contain only water, we can use plastic cells. However, when we are using other chemicals, organic chemicals, these plastic cells will melt. Plastic will dissolve in that particular solution, so cell will damage. Because of that, we are not using plastic cells when we are using organic solvents. So we use glass and quartz. When we are dealing with UV, we have to use quartz. Quartz will not absorb UV light. Quartz වලින් සාමාන්‍යයෙන් UV light එක absorb කරගන්නේ නැහැ. ඒ නිසා අපි UV light එක වැඩ කරනකොට අපි පාවිච්චි කරන්නේ quartz. සාමාන්‍ය දෘශ්‍යාලෝකයක වැඩ කරනකොට අපි පාවිච්චි කරන්නේ glass. හැබැයි දෘශ්‍යාලෝකයත් එක්ක වැඩ කරනකොට we can use quartz cells also. එතකොට quartz cells තමයි ගොඩක්ම. හැබැයි මේවා හරිම මිල අධිකයි. Very expensive, around 1 lakh. One cell, so very expensive. We have to careful about that when we are using that. Okay. That's the thing about these cells. However, in single beam spectrophotometer, light source will emit light. It goes only one path. It will not divide into two. So light will go through this solution, and here we can see the detector. It will give the absorbance value. This is single beam spectrophotometer. Okay. double beam spectrophotometer, when we are using double beam, there are two light sources also, UV and visible light. However, the light path will divide into two. Divide into two in this instrument. Incident light will divide, or the source of light source will emit light. That light will divide into two. Here we using prism, and there are some mirrors. Okay, this light will divide it into two parts. So one will get from one cell, and other light source will go from other cell. Two sample cells we can include for this instrument, double beam spectrophotometer. Okay. What is the point? Here, there is major disadvantage because always we have to get the blank reading. Because, for example, here we are talking about cobalt 2+. However, this solution is made up from the water. We dissolve cobalt ions in water. So, this solution, if we consider cobalt solution, it contains cobalt 2+ and water. However, we need to measure the absorbance of cobalt. අපිට cobalt ගේ absorbance එක විතරයි බලා ගන්න ඕනේ. water වල නෙමෙයි. හැබැයි water වල තමයි dissolve කරලා තියෙන්නේ. එතකොට මොකද අපි කරන්නේ? We have to get the reading of water without cobalt. Cobalt නැතුව water වල විතරක් absorbance එක කොච්චරද කියලා බලා ගන්න ඕනේ. Imagine here initially we insert water, distilled water. Its absorbance is AW. Now we will introduce cobalt solution. It also contains water. Now we will get that reading is AT. AT means cobalt 2+ and water, both. So we can get the absorbance of cobalt by deducting AT minus AW. We can get the absorbance of cobalt 2+. So every time we have to measure the blank reading. අපිට අපේ ඇනලයිට් එක නැතුව බ්ලැන්ක් එකේ බ්ලැන්ක් එකක් කරන්න නම් මොකද අපි කොබෝල්ට් දිය කරලා තියෙන වතුරේ ඇබ්සෝබන්ස් එක අපිට වැඩක් නැහැ. අපිට ඕන කොබෝල්ට් වල ඇබ්සෝබන්ස් එක. ඒ නිසා අපි සාමාන්‍යයෙන් මෙයාගේ රීඩින් එක ගද්දී සාමාන්‍යයෙන් අපි කරන්නේ මුලින්ම initially we have to include water, distilled water, and we will get the absorbance value. There is a button in spectrophotometer called blank. There is a button. We have to press that button. At that time, it will adjust its absorbance as 0. Okay? So we don't have to calculate this AT minus AW. The spectrophotometer automatically will give the absorbance of water as 0. It will adjust. We have to press this button, blank button. Okay. After that, first of all we have to add water and we will blank the instrument. Now the absorbance is 0 compared to water. Next, at second, we have to add our cobalt solution. At that time we can get the absorbance of cobalt 2+ ions only. So disadvantages of single beam spectrophotometer, මොකක්ද ඒකේ තියෙන අවාසිය? අපිට we have to repeat the blank procedure. Before reading, we have to get the blank, and after that we have to input our sample and we have to read the absorbance. If we need to measure the absorbance of another solution, we have to again blank the instrument and we will add our solution. So again and again we have to blank. However, in this double beam spectrophotometer, for one cell we have to introduce water, and we will keep water every time this cell. We don't change this water containing cell, and we will change this second cell cobalt solution. So automatically this will be given blank reading, and here there is a detector. We don't want to change the blank. again and again in double beam spectrophotometer. One light radiation will pass through the black and other will go through the solution. So automatically the reading will be given the absorbance of our cobalt ions. That's the beneficiary thing in this double beam spectrophotometer. Okay. Okay. Now I will talk about the sample cell, because you have to know these things. Sample cell, I told you it is this type of square shape. Here there are two faces. One face is opaque. This side and this side is opaque. Or light can't go through that surface. These two surfaces. There are another two surfaces. This surface is very clean and transparent surfaces. So light goes through these two walls and light can't go through these opaque walls. These are opaque or not transparent. There are two transparent walls and two non-transparent walls. So we have to handle this sample cell by using these opaque surfaces, because we have to touch this cell when we are using chemicals and when we are put into this spectrophotometer. So we have to handle this cell by using these two matte surfaces or opaque surfaces. However, we should not touch these transparent walls. Transparent walls are very clean. They should be very clean. We don't want to touch. We should not touch that. Okay? Light will go through that clear surfaces. Okay? That's the thing. Okay? You have to remember these things. Okay, now we will move to the experiment. First of all, we have to get the maximum absorbance lambda value of maximum absorbance wavelength of this cobalt solution. However, I will select one of lowest concentrated solution from this series. There are 11 solutions. I will select lowest concentrated solution here, 0.1. I will select 0.1 solution, that is in the volumetric class. Okay, now I will get this sample cell. Initially what we have to do, we have to clean this sample cell. First thing, we have to wash with tap water. Next, we have to rinse it distilled water. Again, we have to rinse it with this particular solvent or solution. We add a small amount, around 2 to 3 milliliters or 5 milliliters, and we will rinse the inside wall of this cell. We will rinse, because in first time we wash with tap water, second time we add distilled water. This solution contains particular concentration 0.1. However, when we add this solution to this cell, it will be diluted because of this distilled water. Because of that, as burette and pipettes, we have to rinse this sample cell also with the relevant solution. Okay. Third one is rinsing with relevant solution, which means this cobalt solution 0.1. So we will rinse, we will clean the this cell. After cleaning, we have to dry this sample cell. How to dry? We will not dry by using oven or desiccator. We will not using that method. We will use acetone, or we have to use tissue papers, because not inside actually. Okay, we have to dry the outside of the outer surface dry the outer surface of this cell by using tissues, not inside. Inside we rinse it relevant solution and we will pour our relevant solution into this cell. We will pour this solution and after that we have to dry before insert into the spectrophotometer. Spectrophotometer එක ඇතුළට දාන්න කලින් මෙයාගේ surface එක අපිට clean dry කරගන්න ඕන. Why? If there are some distilled water or some droplets attached to this outer surface, what will happen? We are dealing with light, so what will happen? When we input or when we introduce this cell into this spectrophotometer, what will happen? The incident light will go through this water bubble, water particle, and light will scatter like this. So reading will be an error. We will get lower reading, but actual reading will be higher. However, light will not come to the detector because of this scattering. මොකද වෙන්නේ? එළිය surface එකේ වතුර තිබ්බොත් එහෙම මේ වගේ තැන් වලින් මේ විදිහට මේවා scatter විසිරලා යන්න පුළුවන් detector එකට යන්නේ නැතුව. Because of that we will get lower intensities because of this scattering. So we have to dry the surface of this cell before introduced into the spectrophotometer by using tissue papers. Okay. Now we introduce it into the spectrophotometer. Okay. Now what should we do? If we are using this double beam spectrophotometer, we have to include distilled water sample here and we have to input our sample here. However, when we are using this single beam spectrophotometer, initially we have to input distilled water sample and we have to blank the instrument and next we have to add our sample. Okay. So we have to get the maximum absorbance wavelength. Maximum absorbance wavelength. Okay. To find that, there is a adjustment in spectrophotometer. We can change or we can select wavelength. We can change the wavelength of this instrument. Okay. Initially, now I will put my sample cell into the instrument. Initially, I will adjust the wavelength as 200. Just imagine 200 and I will observe the absorbance value. Here detector. Here I will get absorbance value. Now I will erase these diagrams, okay? You got the information. Everybody. Okay. Now I adjust lowest wavelength 200 UV region and we will observe the absorbance. I will plot a graph with respect to lambda max. Here lambda or wavelength in nanometers, lambda. Here absorbance versus lambda. I plot a graph. Initially I used lower wavelengths, so here 200. Its absorbance value will be here, lower absorbance values. Now I will increase the absorbance values. 201, 202. Likewise, I will increase the lambda max. So absorbance value will be increasing gradually when I am increasing the lambda max value. Okay. Here imagine in some points, in one point we will get this type of graph, finally we will get a bell-shaped graph. We will get one point we can see there is a maximum absorbance wavelength at one point. What we did? We increased the wavelength and we will observe the absorbance. 202, likewise 250, 300, likewise we will increase up to 700 nanometers visible region. From UV region we will adjust the knob, this adjustment, and we will increase wavelength up to visible region, and we will observe, this is 700, we will observe this type of graph. At one point absorbance will be maximum. This called maximum absorbance, and this called maximum absorbance wavelength. In other words, lambda max. This is the lambda max. So we calling this method is scanning. We scan the lambda values, scanning. We scan the lambda wavelengths and we found the maximum absorbance wavelength. So here, in practically, increasing wavelength one by one, 200 to 201, 202, it is time consuming. So in practically we increase the lambda max value by 5 by 5, 200, 205, 210, likewise we increasing 5 by 5. However, when we are increase the gap, here 5, gap is 5, here gap is 5. Someone can say 200, 210, 220, likewise 10 by 10, the gap is 10. When we increase in the gap, it is very harmful for our experiment, because we will miss the exact lambda max value. For example, consider we will increase our lambda max value by 10 by 10. Imagine the lambda max should be in between this 20 and 30. Just imagine, this is example. Lambda max should be here. However, when we increase in 10 by 10, what will happen? We will get this type of data. So that graph will be like this. Lambda max will be here. So we will read the errorful calculations, errorful observation, because we increase the gap. So the exact method is we have to increase the lambda values or wavelength one by one. At that time we can get the accurate measurement. Okay. Now we got the lambda max value. Okay. After finding of this lambda max value, we will do the experiment for Beer-Lambert law validity. So now we calculated, or we observe the lambda max. Now we can now we will introduce these 11 solutions separately into the spectrophotometer, and we will observe the absorbance. අපි දැන් මොකද කරන්නේ? මුලින්ම lambda max හොයාගත්තා. lambda max හොයාගන්න ඉතින් ඒක වැඩි කරලා මේ විදිහට graph එකක් යන්න. දැන් lambda max හොයාගත්තට පස්සේ we can fix the lambda max value. Now we know the lambda max, we will fix that in the instrument. Imagine this value is x. Lambda max is x. Imagine that. Now this is our spectrophotometer. I will fix x. I will fix this x value. I will not change anymore this absorbance. Now I found the lambda max. Okay. Now I will introduce these 11 solutions, these 11 dilutions separately into this instrument. I will calculate the, I will observe the absorbance value, and I will plot a graph. Here concentration, here absorbance. Here you can see initially it has lower concentrations, that means concentration lower means absorbance also very low. Points like will be here. When we increasing our here 0.05, here 0.1, here 0.15, likewise when we increasing the concentration, absorbance also will be higher. At one point, up to one point, we can observe a straight line. We can see a straight line up to one point. Up to one concentration we can see a straight line. After that point, beyond that point, this linearity of this straight line will be not go further, it will be produce a curve. It will not a linear anymore after one's concentration. So if we observe or extrapolate that concentration into absorbance axis, absorbance axis we can see clearly this will be 0.7. After 0.7 it will be not linear. So by using this experiment and this graph, we can prove that the Beer-Lambert law is validity range is 0 to 0.7. After that it will be not linear. Not linear means it will be not valid after that concentration. නේද? ඒ කියන්නේ Beer-Lambert law එක රඳා පවතින්නේ 0.7 අතර absorbance value වලට සාමාන්‍ය වැඩි කරන්න යනකොට absorb කරන ප්‍රමාණය වැඩි වෙනවා. ඉතින් එක පොයින්ට් එකකට පස්සේ අපිට පේනවා මේක පොයින්ට් එකක් දක්වා රේඛීය ප්‍රස්ථාරයක් තමයි ලබා දෙන්නේ. හැබැයි ඒ පොයින්ට් එකෙන් පස්සේ ඒකේ රේඛීය බව නැති වෙනවා. වක්‍රයක් හදනවා. වක්‍රයක් කියන්නේ linearity එක නැති වෙනවා. Loss of linearity of this curve means it will not obey the Beer-Lambert law anymore. That's the thing. That's the aim of this experiment. Okay. I think I will explain everything. Here we selecting when we are going to measure this lambda max value, we selected lower concentration because if we select higher concentration, its absorbance will be higher than this 0.7. So we will not get the accurate value. So we will use lower concentrated solution to measure this or observe this lambda max value. That's the reason. Okay. Those are the things you have to remember. I think I explained everything, cleaning methods and everything. Okay. When we are using this, preparing this dilution series, we are using volumetric flask. We have to clean them. First of all, we have to use tap water, next distilled water. Okay. After that, when we preparing these dilutions, we have to use pipettes. Up to 2 decimal points, they given the values. So we have to use pipettes. Okay. Pipettes and burettes. When we are using pipettes and burette, we have to rinse it with the relevant solution. අදාළ දාන්න යන කෙනාගෙන ඒවා rinse කර ගන්න ඕන. And sample cell also, first tap water, next distilled water. After that we have to rinse it with relevant solution. However, we will not dry in oven. We will use tissue papers to dry outside. Okay. I explained everything. I think this is the end of this experiment number 7. Okay. Now every experiment I discuss, I hope you learn something. This is a revision actually. I can't explain the results anymore because it is unethical, because in next year, next batch also should go through these experiments. If I reveal the calculation parts, so it is unnecessary thing. It is not ethical thing. So this is my limit. If you got something from these videos, please subscribe my channel and please share these videos and stay with me because I will upload more videos about university level.